Welcome to submodule 2.3. Today I'll be talking you through two more applications beyond QKD that we can explore in the Quantum Network Explorer. My name is Janice, and the topics that we'll cover today are quantum state teleportation and blind quantum computing. First up, quantum state teleportation. What is it and why would we want to use it? Quantum state teleportation is an application where some sender has a quantum state. They may or may not know what the state is, and they want to send it to a receiver. As I told you about in submodule 1.2, we have this thing called the no cloning principle, meaning that we cannot just make a lot of copies of this state and try to send them one by one. We only have one shot to do this, and that's where quantum state teleportation comes into play. Here, a sender uses entanglement with a receiver to send or teleport their state across. So how does this work? Let's say we have two end nodes, one called Alice and one called Bob, and Alice has a quantum state, and they want Bob to have this quantum state. For this, we need an entangled link between Alice and Bob. So this can be established, for example, by having Alice create an entangled pair and sending one end to Bob, or the other way around, or maybe from some kind of mid station like a hub, sending both ends to the end users. Once this entangled link is established, which is a generic link, so we can do it or try multiple times without affecting the state that Alice wants to teleport, then the sender, Alice in this case, can perform some local operations to also entangle her end of the entangled link with the state that she wants to teleport. Then she performs measurements on both of these qubits and sends the outcomes of the measurements over to Bob. Then all Bob has to do is apply some local corrections to his qubit, which is the one end of the entangled link, and with that, somewhat magically, the state that Alice had on her side is now teleported onto the qubit that Bob holds in his memory. So as an overview in QNE, the input for this application would be the quantum state that you want to teleport, as well as the network configuration. In the network configuration, you can specify where you want the location of the sender and receiver to be, as well as the quality of their nodes and maybe the nodes between them, if there is any, as well as the quality of the links between them. And this will determine in the end the quality of the state that the receiver gets. The steps that they need to perform is creating entanglement between the receiver and the sender. Then the sender performs local operations and measures their qubits, sends the outcome of the measurements to the receiver, from which the receiver applies corrections. Then as the output, we will have the quantum state at the receiver with some fidelity, and this fidelity tells us about the quality of the state, meaning how close the state at the receiver is to the state that the sender had initially. And this will depend on your network configuration. The more imperfections you have in your links and your nodes, the lower the fidelity will be. And it's 1 if everything went perfectly, and it will go down the more imperfections you introduce. So now let's see what this looks like within QNE. I've just shown you what the inputs are, and this is what it looks like on the website. If you select the state teleportation application, this is what it looks like. We are looking at the Europe map, and right now our sender is located in Paris and our receiver is in Copenhagen. But we can also change the locations. For example, if we want to put our receiver in Innsbruck, we drag and drop the receiver to Innsbruck, and now we've changed the position of our receiver. We can go to the next step and we can change all of our network configurations. So we can change the quality of our nodes and of our channels. Right now we can keep everything to perfect to see what the application runs like. In our next step, we choose the qubit state that the sender wants to teleport to our receiver, and we can do this by choosing any of the existing input states or by changing the angles in the block sphere. Let's choose a plus state to teleport. Now we are ready to start running the protocol. So we click run and we wait for our experiment to be running. All right. We start the process animation and we see that at first they start creating an entangled link. We send over our corrections from the sender to the receiver. This receiver can perform the corrections, and with that the application is finished. So now we can look at our output. Now we see that the state that is teleported was indeed the plus state as we chose in the beginning. Our network configuration was perfect, but if we had chosen to make any of the nodes or the links imperfect, this state would be slightly different. And here at the bottom we see that our fidelity is 1, meaning that indeed the state that we teleported was perfectly the same as the state that we tried to send. But again, if our network was imperfect, our fidelity would be less than 1, showing how big the overlap was between the state that we wanted to teleport and the state that we ended up teleporting. The second application that we'll talk about is blind quantum computing. In blind quantum computing, we can perform a full quantum computation remotely without needing a quantum computer. And we can do this while keeping the computation hidden. This can still scale up the quantum computing usage, as any client with smaller quantum capabilities can connect to a larger quantum computer and still have all of the capabilities as well as security. So how does this work? It works in 2 main steps. The first is called remote state preparation, and the second is based on measurement-based quantum computing. In remote state preparation, the client has control over a state at the server using entanglement and measurements. So when the server initializes a qubit in the memory and then sends out a photonic qubit that is entangled to this state in the memory, and the client measures this in a particular basis, then it can have control over the state that the receiver has in the memory without the server knowing what the state is. Then, measurement-based quantum computing is an alternative to the more well-known gate-based quantum computing, where instead of having your qubits and applying gates on top of them to manipulate them, we actually take multiple qubits and arrange them in what we call a graph state. And instead of performing gates on them to manipulate them, we measure part of the graph to manipulate other qubits in the graph. And this also works by creating entanglement between the different parts of the graph. So in our example that we'll look at in QNE, we have 2 qubits that are connected with a controlled Z operation to entangle them. And then measuring the first qubit will have an effect on the second qubit. So the blind quantum computing protocol works by the server sending out the entangled photon, the client measuring it in a particular basis and thereby performing remote state preparation on the server. Then the client tells the server to prepare all of the qubits that the client has remotely prepared into a graph state by applying controlled C operations between the nodes that the client specifies. And then next, the client will ask the server to measure all of these qubits one by one in particular bases. The server then sends back the measurement outcomes and they go back and forth until all of the qubits are measured and the computation is performed. In QNE, the input for this application are the angles that define the computation. These angles will be the angles at which the server is asked to measure. And then there's also angles for 2 angles and 2 bits that are used to encrypt the angles that are sent to the server such that it doesn't learn anything about the computation that the client wants to perform. These do not change anything about the outcome of the computation, but ensure for the blindness. You can randomly choose them, and that won't change the outcome. So again, the steps are performing a remote state preparation by having the server and the client establish entanglement, and the client measuring in a particular basis. This is performed twice, as we are remotely preparing 2 qubits in this example. Then the client sends the first measurement angle over to the server measures it and sends back the results, and this is also repeated twice for both of the qubits. Then, as output, we have the state at the receiver before the final measurement, and the final measurement outcome. And this is the most important part, because this is the output of your computation. So now let's see what blind quantum computing looks like in our QNE website. We have again the Europe network, and I've put our receiver here in Paris, and our server is located in Delft. In our next step, we can again work on the network configurations and put any imperfections in any of the nodes or the network channels. And then our input are alpha and beta. These define the computation. Let's keep alpha at 0, and we can put beta on 1 pi radians. The other inputs are theta 1, theta 2, R1, and R2. These are all used to encrypt the angle that the client is sending to the server. These do not change the output of the computation, but have an impact on the blindness. So we can choose these randomly, and it won't change anything about the computation. So also let's set theta 2 to 1. Let's keep R1 at 0 and put R2 to 1 as well, and then see what happens. Here is an overview of our inputs, and let's run the application. Let's see what this looks like. Our first step is preparing the states, remote state preparation, for which we use entanglement. And we do this one other time because we want to remotely prepare 2 qubits. Now we finished the remote state preparation, so we can send our first measurement angle from the client to the server. Here the client asks the server to measure, and the server sends back the measurement outcome. Then we can calculate the measurement angle for the next qubit to be measured, send this back over to the server, and the server measures and sends back the measurement outcome again. And with that, our computation is finished. So now let's look at our outputs. We see here the final state at the receiver. This is what the state of the qubit was, of the final qubit was before the last measurement outcome. And here are our measurements outcome. The last measurement outcome, M2, is the most important because this is the output of our computation that the server sends back to the client, which they can correct based on measurement outcomes of previous qubits. And with that, we have finished our computation. So to summarize, today we learned about 2 applications beyond QKD, which were quantum state teleportation, in which a sender can teleport a quantum state to a receiver without needing to know what this state is. And we also learned about blind quantum computing, where a client can connect to a quantum server to perform securely a computation that it wouldn't be able to perform on their own, using remote state preparation and measurement-based quantum computing.